Very well. So let me first say a few words about where we got stock last week. So suppose we have a space then the set of the homotopy classes of maps of spectra from sigma infinity x to a ring spectrum y is again a ring, and we we prove this apart from the distributive property, and, which is basically saying that we have two operations, the sum and the product, and that those satisfy the usual left and right distributive identities. Now, I overthought it. In fact, the distributive property is quite straightforward. Let's see this. So let's let's recall the definition of the product of two maps from sigma infinity x to y. Well, here it is. Well, so the to prove one of the identities, we need to prove in fact, the proofs of both identities are identical. It would suffice to prove it would suffice to prove the same identities for with the smash product instead of the dot product. So basically, if the smash product is bilinear, then we just use that the fact that the maps of the Homs induced by maps of spectra are maps of abelian groups, so they preserve the operations. And in particular, these two arrows induce maps of the Homs in the homotypic category of spectra, which preserve both operations. Okay. Let's look at the statement. Does the statement make sense? Does everyone agree? And then the bilinear property for the sum of two maps is well, pretty much straightforward. So we have, and what's more convenient, it's true for arbitrary spectra. We don't need to assume that one of the spectra is a suspension spectrum. Suppose I have two maps fg from x1 to y1 and h from x2 to y2, then Then I have two ways of passing from okay, no. I can double by 1, no, what I'm writing, no, x1, x2, so these are the starting spectra, the source spectra. Okay, so I need to double, here I double x1 smash x2, and here I double x1 wedges 1, x1 smash x2. Okay, so these are isomorphic. Moreover, they're naturally isomorphic. Okay, so I'm using the fact that this is a natural transformation and replace replace x's with y's, y1, wedge, y, no, y1, wedge, y1, smash, well, this one's supposed to be a smash, sorry, I started off the wrong foot, x1 smash x2. This is the source spectrum for all maps. And so this one is supposed to be a smash y2, and then we map everything into y1 smash y2. And the top row gives me f1 plus f plus g smash h, and it's the other way around. The top one gives me f smash g plus f smash h plus g smash h, and the bottom one gives me the f plus g smash h. Well, the square in the middle commutes because the isomorphism, the isomorphism, the vertical isomorphisms are part of a natural transformation. So they commute with maps induced by maps, and the left triangle and the right triangle. Why do they commute? Well, I would say it's something which it's straightforward by deciphering the definitions. Okay, so the distributive property is not much more difficult than the other properties. Well, yes. This one is valid for all spectra, not necessarily those that come from spaces. But then we use it for to prove that if we have a spectrum which is a comonoid with respect to the smash monoidal structure, then the set of maps from this spectrum into a ring spectrum is a ring, and it's a monoid by general nonsense, and the rest of the ring structure basically comes from from the fact that spectra is an additive category, and the product is bilinear, as we've just seen. And the reason is that the smash product becomes the dot product after we compose with these two maps. We have the smash product F smash G, which is fine, but the result is a map from the smash to the smash. If we want a map from the spectrum to the spectrum, we need to compose with this one and with this one. Okay. Are there any questions? Now let's let's prove the Poincare duality theorem. But first, let's briefly review the notation which we probably saw at some point, but let's even so let's remind ourselves of this piece of notation. Okay, so suppose we have x and y, and suppose both are spectra. We know what the homotopy classes of maps are. Now, if I put an integer r, what do I mean by that? I mean the homotopy classes the homotopy classes of maps of degree r in other words, I consider the homotopy classes of maps from X to Y let's to y. Okay, y shifted by r n is okay. So I need to put a minus here. Y and minus r. Okay, so in other words, I consider maps from X to Y of minus r, and this is a spectrum, and then I just consider the usual homotopy classes of maps. Okay, so in other words, this is y shifted by r to the left or to the right. For example, if r is 1, then y minus 1 of 0 is y minus 1. Yes, by r to the right. Okay, so now we remember or know that what this thing denotes. Okay, so suppose E is a ring spectrum. And X is a space. Then the non-reduced cohomology of X with coefficients in E is X plus. And similarly, the non-reduced homology of X with coefficients in E is just the homotypic groups of the product spectrum. E E smash the sigma infinity of X plus. Recall that X plus is not quite the same as X. It's X plus 1 point. And we saw last time why we need the extra point. We want this sigma infinity of X plus to be a comonoid in the smash monoidal structure. If we just have space, we don't necessarily get a comonoid, but if we have a space plus, then we do. Okay, now the theorem is as follows. Suppose M what we will see today is not the most general version of the theorem, but it's still the proof contains all the main ideas. So suppose we have a smooth compact manifold without boundary. There is a version with boundary which I will also mention, but I will not give a detailed proof because we because it's something which I would like you to think on your own, to think about on your own. Smooth, compact, no boundary. Suppose that okay. So first, let me take E a ring spectrum. And then suppose that the normal bundle of M in some sphere is orientable. Well, we take an embedding of M in some sphere, and well, it's not too hard to see that if we increase the dimension of the sphere by 1, this preserves orientability. Okay, but first let's finish stating the theorem. Okay, so the normal bundle is E orientable. Then we have an isomorphism between the cohomology of M and the homology of M in the sense of this definition. Just as in the classical case, when E is the Eilenberg-MacLane spectrum of Z or the additive group of another ring. Well, okay, so this is what we want to prove, and let's prove this, and then we'll we'll discuss a few remarks. Okay, so basically we already have all ingredients. So we we embed M plus in the same sphere so that the extra point goes to the infinity, where we choose one point of the sphere and declare it to be infinity and declare the complement to be Rn. Okay, so now we use okay. Let me be a little more careful. And write the sigma infinitive. Okay, so as we know, the dual of the spectrum of the suspension spectrum of M plus is the same as the dual the suspension spectrum of Sn. So we have Sn minus M plus is the same as Rn minus M. Very well. So this is the this is the Alexander duality, and we saw this at some point. Very well. Okay, so in other words, the dual is more or less the same as the suspension spectrum of Rn minus M. Let's take a small tubular neighborhood with respect to, for example, the standard metric on Rn. Okay, so Rn minus U is a homotypic equivalent to Rn minus M. Well, so we have what do we have? We have Rn minus U. Well, Rn minus U can be thought of a CW complex because what do we do? We just take Rn and remove something which is the interior of a smooth manifold with boundary. So the R minus U is also a smooth manifold with boundary, hence it has a CW structure. Okay, so okay, so we have this we have this Gauss-vibration sequence for spaces. So this one is for spaces. And so we have a similar Gauss-vibration sequence for spectra. And so this one is for spaces, and this one is for spectra. So basically, we would take this one and replace and insert sigma infinity everywhere, and this is it. Very well. Now let's observe that the spectrum, well, the space Rn is contractible, so the suspension spectrum is contractible. So we so the arrow this one. the arrow marked asterisk is an isomorphism. Why? Well, for example, one can apply the homotopy groups. We know that the homotopy groups are the result of applying of taking hom from the sphere to the long exact sequence. Very well. So the to the long version of the cofibration sequence, when I have here the suspension of the suspension of everything, and here the suspension minus one of the same thing. Okay, so when I apply a hom from the sphere spectrum, I get a long exact sequence. But every third term will be zero, so all the remaining ones are isomorphisms. In other words, the suspension spectrum of Rn minus u is isomorphic to the suspension spectrum, well, to a shifted suspension spectrum of, Rn by Rn minus u. Okay, so the suspension spectrum of Rn with Rn minus u collapsed is up to a shift, the same as the suspension spectrum of Rn minus u, which is the same as the suspension spectrum of Rn minus m. Okay. Well, now let's remember this. So what do we get here? We get suspension plus 1, and then no, sorry. Okay. Let me write it. Let me write this again. Minus m of m plus. No, I'm writing nonsense again. Let me think. Okay, I have this spectrum, the suspension spectrum of Rn minus m. I want to express the answer in terms of well, in terms of this spectrum. So from the formula we basically conclude that so we have this formula, and the dual spectrum of M plus is minus n plus 1 of n minus m. And then by what we've just seen, we have okay, so we have this equal this, and so the result is the same as infinity plus n of Rn minus u. I've just taken this this formula and added n to both sides. And this is the same as the Thom space of the normal bundle. So, by the Thom isomorphism theorem, by the Thom isomorphism theorem, we have the following thing. By the Thom isomorphism theorem, if I take the reduced homology of the Thom space, I get the same thing as get the same thing as the reduced homology of M, but up to a shift. Let's calculate the shift. Let's see what how the shift affects the cohomology. Well, the result is basically the same as for spaces. So the first thing that happens is k plus n sigma infinity of the Thom space well, this is the Thom space of the normal bundle, and same here, the Thom space of the normal bundle. Okay, so well, what's the rank of the normal bundle? Yes, so the rank of the normal bundle is m minus n, no, n minus m, so we have E, okay, E tilde, no, E, so this, we want to apply the Thom isomorphism. So we need to write E without the tilde. The Thom isomorphism is between the non-reduced cohomology of M and the reduced cohomology of the Thom space. So we have E k plus n minus m of the manifold M itself. So this is the place where we use the Thom isomorphism. And, well, which is the same thing as E k plus m of the manifold itself. Okay, so by calculating the cohomology of this thing, we just get the cohomology of the manifold M. Okay. Now, now let's do the following thing. Okay, so the EK of this spectrum sigma infinity plus n tom is the same as EK tilde of this spectrum. D sigma infinity n plus. And this is the same as D sigma infinity n plus E minus K. Here we remember that the sphere spectrum is the unit, and we just insert the sphere. We can insert it anywhere. So we insert it here. And now we use the fact that for finite CW complexes, the suspension spectra are precisely the two elizable objects. So the dual of this is M plus itself. So we, what do we have? We have M plus, blah, blah, blah. And, sorry, so this one is K, or minus K, yes, minus K. So this one is minus K. And here I need to write minus K as well. Let me rewrite the whole thing. S sigma infinity M plus smash E minus K. Now what is this? This is the same as E minus K of M. Okay, so let's look at this board and this board. My claim is the two boards are already enough. They contain everything we need. So we have that this thing is isomorphic to E, K plus M on the one hand, and lower E lower minus k on the other hand. So we just set I equal minus k, and we get precisely the Poincare isomorphism. Okay, are there any questions? Okay, so we have this formula on the one hand, and this formula on the other. Both these are equal to the same thing, so they're equal to each other. Okay. Well, and this is the Poincare duality theorem. Are there any questions? Okay, so let's see what happens when the manifold is still compact. So suppose that M is smooth compact. Suppose that the normal bundle is orientable with respect to some ring spectrum E. But this time we do not assume that the boundary is empty. The boundary may be non-empty. So so what do you think happens in this case? Well, in this case, we have two isomorphisms. we have two authors, and so one isomorphism each. And these are well, basically so suppose M is the dimension we have this formula, and a similar formula for the cohomology. So we have two formulas. The first one is an isomorphism between cohomology mod boundary and homology, and the second one is similar, but we have an isomorphism between just cohomology and oh, sorry, no. Yes, and just cohomology and the homology mod the boundary. Oh yes, thank you. Yes, exactly. That's the whole point. So the if the boundary is empty, both isomorphisms are the same, and they coincide with the one we've just constructed. On the other hand, if the boundary is non-empty, then we have two different isomorphisms. Okay, and as I said, I don't want to prove those in class. I would like you to think about those on your own. And the proof is very similar to, well, there are two proofs, and both are similar to what we've just seen for in the case when the boundary is empty. Are there any questions? Okay, well, in this case, let's have a 20-minute break, and